So I have the integral from minus to positive infinity of sine of x over x times x squared plus 1. And I want to evaluate it using the residue theorem. So the first thing to do in such case, when you have a sine of x or a cosine of x in the nominator, you write it as the imaginary, respectively the real part of e to the ix. Okay, imaginary part if it's sine of x, and real part if it's cosine of x. Okay, it would be like something like that. Okay, you would have a real part. Okay, but here that's not the case. Here we have the imaginary part. That will be much simpler to deal with. Yes, so that should be your first reflex. Then, as usual, we will try to find the poles. So we will set the denominator equal to 0. So x times x squared plus 1 is equal to 0. That means that our poles are at x is equal to 0, plus and minus I, okay? And now we can see that we have a pole of order 1, that is that everything in the denominator is to the first power, okay? We have nothing squared, okay? Or to the third or fourth or I don't know, the 100th power. We only have everything to the power of 1. That means that we can use the formula for poles of order 1, which says that if you have a fractions, the top of the fractions remains the same, and the bottom we just take the derivative of it. Okay, so we will take the derivative of x times x squared plus 1. Okay, and so x times x squared plus 1, we can rewrite it as x to the third power plus x. And so here if we take the derivative, it's easy because those are polynomials. So we get 3 times x squared plus 1. Okay, and that's at the above the fraction bar will change nothing, so we still have our e to the ix. Okay, which comes from here. Okay, which is if you take the imaginary part, we will get our sine of x back. Okay. Yes. So now our three residues, if we compute them, so at 0, plus and minus I, we get respectively 1 over minus 2 times e, and e over minus 2. Okay. So e, I mean here it's the exponential, but to the first power. Okay, not to the. It's not. We don't have e to the x. We have e to the 1. Okay. It's just that. Okay, so now we are going to choose a counter integral, and we are going to do it in the upper half plane along the along a circular path, so along the upper half circle, basically in the counterclockwise directions. Okay, like that. Yes. Why not in the bottom half plane in this sense? We'll see that later. We need to choose the first option because otherwise we cannot prove that the part along the circular axis, so the part number 2 here, so this part here, we could not prove it if it's in this sense that it converges on the tree and that it vanishes. Okay, we'll see that in a moment. So the first part along the real axis, so from minus to positive infinity, so this part here, will be our original integral, so that goes from minus to positive infinity. And our second part, so which is this, like I said, this circle path, we will let x be equal to r times e to the pi I t, where t is between 0 and 1. Okay, r is the radius, which will tend toward infinity, and e to the pi I t represents a circle. Okay. And if we let t be only between 0 and 1, it represents half a circle from 0 to negative 1 in this sense. Okay, if t would be between 0 and negative 1, I think something which we should do if we go into the bottom half plane, then yeah, we would have from 0 to negative 1 through the bottom half plane, but that's not the case here. And our dx is pi I times r times e to the pi I t dt. Okay. So again, as in the previous videos, we don't really need a lot of things. What we only need is this exponential part. So with the e to the I x or e to the I r e pi I t here, if we choose x is equal to r times e pi I t. Okay, but you can still change everything with respect to t. Okay, so we have the integral from 0 to 1 because t is between 0 and 1. Here in the denominator, we can replace everything with x with this r times e to the pi I t, and the dx, we can also replace it with this pi I r times e to the pi it dt, okay? But as said, this is not the main focus. That's not the important part of this process. The important part is that you write this e to the ix as e to the IRE pi it, okay? So e to the IR times e to the pi it, okay? So you have an exponent inside an exponent, okay? Because now this e to the IRE pi it, you can write it using Euler's formula. So we know that e to the theta I is equal to cosine of theta plus sine of theta, okay? So you can write this e to the pi it inside the exponent as cosine of pi t plus sine of pi t, okay? We have the I here, and so everything else is our theta, so pi t is our theta. So it will be cosine of pi t and plus I sine of pi t. And we still have our I under r outside of it here. Now we can take the I inside and we have, so e to the r stays outside. We have times I cosine of pt, okay, the I is here, minus sine of pt. I don't know why there is something here. Yeah, it's a sine, okay. Maybe I will try to... yeah, I don't know why I did that, but yeah, so it's minus sine of pt. Why minus? Because there's an I here and an I here, which comes from Euler's formula, so it's I squared, so it's negative 1. Okay, so you have minus sine of pt, okay? So now, yeah, so now you have rewritten it like that. And now we know that sine of pt will always be greater than 0 for all t is between 0 and 1, because as said, we go like this. And we also know that sine is generally on the imaginary axis, while cosine is on the real axis. And so if you are in the upper half plane, the sign here will always be positive, okay? In the bottom half plane, if that is the real axis here, and that is the imaginary axis, in the bottom half plane, it would be always negative. But here, t is between 0 and 1, and not between 0 and negative 1. So, yeah, sine of pt will always be positive. And we also know that e to the I cosine pt, so if we consider this part, is bounded because we have an I here, okay, so it's e to the I theta, so this is bounded, okay, so we don't care about it. Because e to the I theta is bounded by definition. Here it has a radius of 1 by definitions, so this is not the problem. We know that r, our radius, will go toward infinity as our half circle gets larger and larger. And so we know we get the following: e to the minus r times sine of pt, okay, because again the cosine part is bounded because there's an I in front of it, so we don't care. And so what plays a big role is this e to the minus r sine of pt. Yeah, so the minus comes from the I squared that we got before, like here and here in front of the sine of pi t. And we know that r will always be positive because a radius always has to be positive. It is a geometric distance, so r will always tend toward positive infinity. It is not possible to have a negative radius, so negative infinity is not even possible. Yeah, and our sine of pi t, as said, is always positive. So that will ensure that we will always have e to the minus something, okay? We have the minus here and the positive here, so it will stay minus, okay? If that part here would be minus, which would be the case if you had chosen a contour integral in the lower half plane, where sine along the imaginary axis would always be negative, okay? And t will be between 0 and negative 1, like that. If you had chosen that, then sine of pi t would always be negative, so we would have negative here plus negative here, and it would be positive, and so we would have e to the infinity, okay, because the radius again is always positive, and so that would diverge, and so we would not be able to make that integral along the circular axis vanish. It would not be possible. That's why we need to choose the integral, the contour integral in the upper half plane and not the lower half plane. That's the reason why, okay. So this is very important. I really want to emphasize that we choose this part because we cannot choose the other part. If we choose it, our integral doesn't converge, and then we cannot proceed. That's why we proceed like that, okay? Because we need our integral to converge along the circular path. We need to make it close to 0 as r gets larger and larger. And so if for that we need a negative exponent in front of the r, and if that's not the case, we cannot proceed. And yeah, we need to choose another path. Okay, so that's the reason why I said at the beginning that we need to choose the path in the upper half circle. Okay, I really hope that you understand what I'm saying, because this is very, very important. Yeah, so as said, we have a minus here, and sign of pt here is positive, and r is also positive, infinity. So we get something like e to the minus infinity, which is an exponential decay, and as I said, this will tend towards 0. And so that means that the whole integral of part 2, so the whole integral of part 2, okay, so part 1 is the part along the real axis, okay, so from negative infinity to positive infinity, and the part 2 is the part along this circular path in the counterclockwise directions. And now we prove that this thing will tend to 0 because there is an exponential decay, okay? So this part 2 goes to 0. So why is that important? Because now we can use the residue theorem. So part 1 plus part 2. So our counter integral are equal in this case to our original integral, so the part 1 is our original integral from minus infinity to positive infinity, and our second part is, as I said, 0, okay? Well, that's what we prove here. And now we can use the residue theorem, which states that that is equal to 2 pi I times the sum of the residues inside our contour. Okay, so we have our 2 pi I here, and the residues that are inside the contour, well, we only have the pole at plus I, which is somewhere around here, only the pole at plus I, because negative I would be in the lower half plane, which we don't need here for this case. So this is our first pole. The second pole is 0 here, which is which lies on the real axis. But be careful here. 0 is only half inside our domain, because I think you can see it clearly. Like we have the real axis, and here is 0. And let me pick another color. Yes, so this is a contour, and I think you can already see that only half of it is inside, the other half is in the lower half plane, and that's why we will only take half of this pole, of this residue, because in fact only half of it is inside our domain. Okay, in fact, if you have only a certain percentage of the residue that lies inside your domain, you need to only take this certain percentage in your calculation. Okay, so I don't know, if 30% of the residue is inside your domain, maybe there is a contour integral that's strange, then you will only take 30% of that value for the calculation with the residue theorem. Okay, so here it's half, so we only take half. Okay, that's why there's a 1 over 2. In fact, it's this 1, but we take half of it, so 1 over 2. So yeah, 50% basically. And that is third value here is the residue for positive I. Okay, if I did no mistake, yeah, I think it's correct. If you insert positive I here in this e to the ix over 3x squared plus 1, we get this value here. So 1 over minus 2 times e to the first power. Yes, and so now we can multiply that with our 2 pi I. And also notice here the 2 pi I are positive, so we don't have negative 2 pi I. We would have negative 2 pi I if we had only the lower half plane, a thing which, as said, we cannot do, otherwise it would not converge. But in the lower half plane, given that our counter integral would be clockwise, okay, we start from minus infinity, we go to positive infinity, and then we go like that. It would be clockwise, and clockwise in math is a negative, and counterclockwise it's positive. If you go like that, which is clockwise, it is negative, and like that, which is counterclockwise, it is positive in math. It's something very important. So here it's positive because our counter integral, as said, we got in like something like that. Okay, so we start at negative infinity, we go to positive infinity, and then we do a path in the upper half plane in the counterclockwise direction. So we will multiply by this 2 pi I. Okay, really important. I hope you understand what I'm saying. And so now if we multiply it out, we get minus I pi over e to the first power plus pi I, okay? And so now you can factor out the pi I, and you're left with 1 minus 1 over e in the parentheses. So this 1 minus 1 over e, yes, they are here. And now remember that at the beginning we took the our original integral with sign is the imaginary part of the integral that we choose now. So what we only need to do now is to take the imaginary part of the entire result here. So the imaginary part of pi I times 1 minus 1 over e to the first power, okay? So this e is to the first power in the denominator, of course. So if you take the imaginary part here, you see here we have an imaginary number. So it will, if we take the imaginary part, it will go away, and you're left with pi times 1 minus e to the minus 1 power. So which is equal to that thing here without the I. So p times I minus 1 over e. Okay. So this is our final result. Okay. Yeah, so I hope you understand what I did. So the important parts, whenever you have an integral of the form integral minus infinity to positive infinity, also sometimes from 0 to infinity or minus infinity to 0, it also works. Whenever you have something like that kind of integral with sine of x or also cosine of x and something in the denominator, or I said, if you have cosine of x, you need always to convert that into the real or imaginary part of e to the ix, okay? So real part of the same integral but with e to the ix, I hope you can read it, or imaginary part of the same integral but with e to the ix instead of your sign, okay? That's very important because it's a lot easier to deal with this e to the ix than with sine of x or cosine of x in complex analysis, okay? So once you've done that, you take your poles as usual, so you set the denominator, so the thing here in the denominator equal to 0, and you solve, and then you calculate the residues. So you notice if you have a residue of a pole of degree 1, in that case you can use that formula here, so you only take the derivative of the denominator. If it's of higher order, you need to use the more complicated formula. If I remember well, it's something like 1 over n minus 1 factorial times the limit as x approaches our pole, let's call it s, times the nth minus 1 derivative of x minus our pole to the nth power times our function f of x, okay? If n is greater than 1. But here luckily it's not the case, so you don't need to do it. Then you evaluate your residues at the different poles, okay? So here 0, plus and minus I. And again, you be careful that your 0 is only half inside your domain later. Remember that if only a given percentage of your pole lies inside the domain, you only calculate with that given percentage of the entire value for the whole calculations, because only a given part of it is inside, so it wouldn't make sense to take the whole value. Okay, but of course if the pole is entirely inside the domain, like I here for us, it's something like here, negative I is outside but I is completely inside, so we take the whole part of it. Okay, so then the tricky part is to, let me show another color, is to prove that the part along the upper half circle, that it tends towards 0, that you have an exponential decay when the radius get larger and larger, okay? And so that's why we need to be careful about where we do our contour integral, because we need to make sure that we have a negative sign in front of the r, okay? We need to be sure to have something like e to the minus r, where r or radius will, as said, tend toward infinity. If we have something positive, it does not converge, and then we cannot say anything about the integral, and so we cannot evaluate it like that. So that's why we've chosen this upper half plane and not the lower half plane. I really want to insist on that because this is really, really important. So I said to prove that the part along the real axis is your original integral, and the second part you will let x be equal to r times e to the pi I t, which represents a circle of radius r. Okay, this e to the theta I into the pi I t, that is a circle. And so t here will be between 0 and 1 because you are in the upper half circle. It would be between 0 and -1 if you were in the lower half circle. But again, that cannot be done here. So here it's between 0 and 1. So also dx is, you can calculate it, it's pi I times r times e to the pi I t dt. And then you plug in everything in terms of t. But again, the important part, basically, the only part that is important is that you have your e to the I x, which will be changed into this e to the I r e to the pi I t. So you have an exponential inside an exponential, because this exponential inside the exponential can now be rewritten using Euler's formula. So e to the theta I is equal to cosine of theta plus I sine of theta. So you can you can express it in another way, and then you can take your I of the original e to the ix inside this cosine pi t plus I sine pi t, and so your cosine pi t will be bounded because there's an I now in front of it, so it's e to the I theta again, so something that is bounded as seen here. And your sine, now as said, you need to make sure that at the end you have negative sign in front of the r. So if there's a negative sign already in front of the sine pi t and no negative sign in front of the r, your sine of pi t will thus also need to be positive. Otherwise we'll get negative, so positive r. So as said here, luckily this our sine of pi t is positive, so the whole thing will be negative. Okay. And so at the end, if we let r goes toward infinity, we will get our exponential decay, and so the whole integral will vanish. And once that is done, the second part vanishes, so the part along the upper half circle, and you will only be left with the part along the real axis. And so now you can use the residue theorem, so 2 pi I times the sum of the residues, so 2 pi I times the residues computed before. And again, be careful that if only, for example, half of a given pole lies inside the domain, you only take half of it. And then you evaluate everything. And that is your final answer. And here again, I said if your original integral is the imaginary or the real part of the integral you used here with e to the ix. Okay, if it's the imaginary or the real part of it, at the end you need to take the imaginary or real part of it. So here I said you have an I. So if you take the imaginary part, the I will vanish, and we will get a real value as a result finally, which is this pi times 1 minus e to the minus 1. Okay, so that is our final result. Okay, you can notice that if you took the real part of it, you would get 0, which would make sense because here if you would have a cosine instead of sine of x, the whole integral is 0. Okay, because this is I don't remember for which order, but it should make sense that you should get 0 if you had cosine of x instead of sine of x. Okay, I don't know if it is the integral even. No, it is not even, or is it even? I don't care. I don't know. Sorry, but that makes sense that you should get 0 if you had cosine of x instead of sine of x here in this place. Yeah. So I hope that everything was clear. I hope I forgot nothing. And thanks for watching, and I should improve my writing. Yes, so thank you.